Okay, for this video, I'm going to talk about my approach and solution to this IMO problem, which is this year's problem 3. This is a geometric question proposed by Ukraine. And to start off with some other background, how hard it is, well, problem 3 is typically for the harder problems on the IMO, and indeed, in my opinion, this is pretty hard. So if you wonder what this MOHS means, it stands for Math Olympiad Hardness System, developed by one of the past Olympian named Evan Chen. So I rate it as a 40, which is a typical tough IMO problem. And if you want to know how tough it is, well, the average score is probably around 5% on the IMO. And this is also the lowest among the 6 problems on the 2021 IMO. Well, if you think about it, for this average score, you also have to look it in combination with other problems. Like for example, this year's IMO problem 2 was also one of the hardest in the recent IMO problem 2. So that might have dragged people from solving problem 3. So this is also why the average score for this problem 3 was low. But regardless, even if you do this problem in isolation like I did, it was still really hard. And there's also the histogram of this problem on the IMO website, official IMO website. And finally, if you ask me how hard I think it was, well, I took the whole night plus a bit of the next morning in order to solve. So I don't think I'm confident that I can solve it if I were to be in the contest setting. Okay, now let's go to the problem statement. So this is a geometry problem, so there will be like a lot of points, circles, and stuff like that. So yeah, so they give you a triangle, a acute angle triangle, where AB is greater than AC, and this point D is inside the triangle ABC, and it is on this bisector of angle BAC. There are also points E and F, where E is on the line or rather segment AC, and it also satisfies the angle where angle ADE equals to this angle BCD, which is this one. Okay, and how about F? F is on the segment AB, and the angle FDA is the same as the angle DBC. There are also other points like, you know, the like point X, where X is on line AC and CX equals to BX. So basically the perpendicular bisector of this BC, and X is on this line. O1 and O2 are the circumcenters of these two circles, meaning two triangles, meaning the triangle ADC and the triangle EXD. So what this means is that for each triangle, meaning that each set of 3 points, there is a unique circle that passes through all of them, and we simply have the circles of the centers of these two circles. And finally, now we need to prove that the lines BC, which is this base, the lines EF, and also the two centers O1, O2 are concurrent, meaning that they meet at the same point. So for some initial observation, yes, from this angle condition, we can say that yeah, D is on the angle bisector of the angle A. So yeah, and then we see that there are also this angle condition. So yes, we think that okay, we can probably do some angle chasing. The harder part would be to actually make use of some of the points. For example, they define this point F for you, but F seems to be a bit isolated compared to the other points. Like for example, if we are talking about E, then at least there's one circle that is named that is defined after E, but there's nothing about F, and yet we need F in order to prove the statement that we are interested in. So this is what makes this is one thing that makes the problem hard, where you have this point that is not closely related to each other, and yet you need this point in order to prove your statement. And there are also two circles like ADC and ESD that seem pretty random, which is also why this problem is hard, because it's not clear how are you going to make use of it. And finally, how are you going to prove that how are you going to prove that there's one line that, sorry, how are you going to prove that some point lies on the line joining the two centers? There aren't that many like geometry identity that ties to it. Like if for example, if you want to if you want to prove that like a set of 4 points lie on the same circle, then sure, you can use angle tracing. That this is what I mean. But there is not there are not like many identities that that revolve around a point lining on the line joining the two centers of circles. So this is the thing that makes a problem hard. Now, if you are wondering how, before I go to my solution, I should also mention that the thing about geometry is that this is the diagram they give you, or rather you draw it yourself after reading the problem statement. But in order to solve it, a lot of time you have to define new points and new circles and basically new things, and it could sometimes make the diagram really complicated. So later on, when you see my solution, you'll also see that there are times where we just strip off most of the other points and focus on only a subset of the points. So now, yeah, this is my solution organization. So the first thing I did was to get rid of f. But how am I going to do it? I look at where the intersection of EF and BC are. Yeah, because if you can determine what the intersection of BC and EF, then we don't really need F anymore, because we can just operate on this point instead and show that this point also lies on the third line. And then we split into two paths, and first of all, they give us two circles where we are interested in the two centers, and it just happened that these two circles have one of the common points defined in the problem, which is D. And now we are going to determine what the second intersection, which is Z, look like. And the other one is to transform this problem in terms of Apollonius circle, so that we can remove some other points and transform the problem into an equivalent, which is like less, I wouldn't say less complicated, but it's easier to deal with. And we will finish up the solution by using a bunch of some elementary tools, which is cyclic quadratic literals and similar triangles. Okay, so first off, step one. Let me explain again why do we want to remove f? Because again, like what I said before, f is a point that is defined in the problem, that it's not closely related to other points and therefore less useful, but yet we still need f in order to solve the problem. And then we will think about, why do we need f to solve the problem? Because we want to prove that these three lines are concurrent, and one of the lines is defined based on f. So what if we just understand what this line is really about, line EF is really about, without really relying on the point f? Or better still, what if we know what is the intersection of BC and EF like? So we define this point as T, and then we just have to prove that this T lies on O1, O2. If we really want to do that, meaning that if we really want to understand what T looks like, then there's one tool that we really need, which is called Monolous Theorem. So this whole screenshot was taken from this website called The Art of Problem Solving, and it basically says that if you have this triangle, and you have these 3 points, each of them lies on one different side of the triangle, and these 3 points are collinear, meaning they lie on the same line, then you have this equation. This is also an if and only if condition, where if you have this relation, and also the points have to be in certain order, meaning that like if you have P on this if you have P on segment BC and then Q outside and R inside, then you'll get that P, Q, and R lie on the same line. So yeah, these are all equivalent. But this is the thing that we are this is the ratio that we are more interested in. And also that it will also be useful if we can kind of like understand what the ratio would look like, because sure, if we want to make good use of this if you want to make a good use of this equation, then we kind of also want to know that for at least for two of them, what would the ratio look like. So so here we introduce another tool called the ratio of Sine cut, meaning that if you have this triangle A, B, and C, sorry, A, B, C, and then D lies on the line BC, and then we can compute the ratio of BD to DC in this manner. So here there are two ways in order to calculate the ratio of BD to DC. Number one is to sorry, there are actually two ways we can calculate this area, meaning that the area of triangle ABD and triangle ADC. So the first way is that we know that the ratio of these two triangles ABD and ADC is precisely BD divided by DC, because they have this they have this common height, which is the height from A to BC, and therefore the ratio of the area only depends on the side length. The second one is by using sine rule, or rather area of triangle using sine rule, meaning that you have ABD equals to half times this line AB times the line of the line AD times sine of BAD, and the same for its triangle ACD as well. And therefore you can simply equate that BD divided by DC equals to the ratio of this one ABD, this equation divided by this equation, and then you end up with the thing that you need. Okay, the other thing is that so suppose that you have this triangle ABC, and then you draw the tangent from point A, and this tangent meet the line BC at a point T. The claim is that TB divided by TC is the square of AB divided by AC. So how do we get to here? So this one basically relies on a bunch of similar triangles, meaning that we know that this is the tangent. This line TA is a tangent, so the angle TAB is the same as the angle TCA, and therefore we got a bunch of actually not just a bunch, just a pair of similar triangle, and then you get this ratio. I'm not going to go through it. It should be self-explanatory, but if you just do the ratio chasing enough, you should be able to get this identity. Okay, so now getting back to the solution, we want to get rid of f. So how do we do that? So the answer is that we consider the triangle ABC, and we know that f is on AB, E is on AC, and also T is on BC, and then F, E, T are collinear, lie on the same line as our definition. So that means that we can use Monolous Theorem in this form. But how do we get some of these ratios? So in order to do that, we need to go back to this this ratio of Sine cut, and then you get things like this: AD divided basically all this basically all these ratios. To explain a bit more, so AE divided by EC is mainly based on this triangle ADC, and you have E that is on the line AC, and then you basically consider the angle ADE, and also yeah, you basically consider the angle ADE and also CDE, and the same and the same for this one, ADF and also BDF. Um, but this is itself is not enough, so we need to so we need to do a bit better. But then we also know that we also have this condition where the angle ADE is the same as the angle BCD, and then the angle FDA is the same as the angle DBC. So going back to to what we have just now, this one FDA and ADE we can already substitute it with BCD and DBC, which is also why I used these angles instead of the original ADE and ADF itself. As for the angles FDB and also EDC, well, there's a lot of other angle tracing going on, but you can show that with the condition that we have, these two FDB and also EDC should add to 180 degrees. So what does it even mean? If two angles add up to 180 degrees, that means that the sine of these two angles are the same. So that means that we will end up with this. This one itself, along with the Monolous theorem, will give us this TB divided by TC equals to dB square, dB square divided by dC square, and this would directly imply that TD is tangent to the circle DBC, provided of course also that T lies outside of the segment BC. But why does it so? We need to talk about this thing called the phantom point, which I'll talk about really briefly. So here we talk about, like, if T is the tangent, then you have this this ratio TB divided by TC equals to AB squared divided by AC squared, according to this slide. But why does the converse also hold, where if T satisfies this thing, then T is the TA is the tangent line? Well, the one tool is to define a new point T that is a tangent line, and you have that T prime and T satisfying the same property, and therefore T and T prime have to be the same. Okay. So now that we know what T is, we can transform the problem into the following. So everything is the same except we get rid of F, and instead introduce this point called T, which is the point where dt is line dt is tangent to the circumcircle DBC, and then T also lies on BC, and you want to prove that T lies on O1, O2. Now we are still pretty far from being done, because how are you going to show that T lies on O1 and O1, O2? Okay, one tool is to show that TD and T to this second intersection are of the same length. So let's say this point is Z. We want to show that TD and TZ are the same. So this would directly imply that T lies on the line O1, O2, except for the case where these the circles are tangent at the point D. Well, we can go on and on and show that these two circles won't be tangent at the point T. Not point T, at the point D. Yeah, but I'm not going to go through that, because I think that one will be tedious, but it shouldn't be hard, and shouldn't be the focus of the problem, of the solution of the problem. Okay, let's talk about the motivation behind the next step. So now that we want to show that T lies on the line O1, O2, which is the line joining the centers of the two circles, we know that this is the same as showing that T is equidistant from the two intersections of the circles EDX and DCA, meaning that TD and and TZ, which is the other side is the other intersection, are of the same length. But how do we do so, considering that we barely know anything about the point Z? So this means that we have to really learn about this new second intersection. But now the question is how. We know that we know that from these two circles we can use a lot of the properties of cyclic quadrilaterals, meaning angle chasing. And at the same time, we might be also be able to make good use of other angle conditions. For example, the one that is provided earlier on the problem statement. So how are we going to do that? So yeah, let's say this new point is Z, and then recall that we want to show that TD equals to TZ, and here goes into all the angle chasing that we have. And also for your information, because there might be like too many cases, like for example whether the angles should be the same or supplementary, meaning that they add up to 180 degrees. When you deal with things like this, it might be better to use directed angles, meaning meaning that you consider the angles in this form which is like xz. This angle xzzd is the angle that you need to move counterclockwise from xz to zd, and then we will have like xzzd equals to xeed if and only if xdez are consecutive. Yeah, and then these are basically just angle chasing, which I am not going to go through individually. But in the end, what we are interested in is that is this identity where xzza is the same as bcda. Now that we already have this, but so what? How can this be useful? In order to do that, we need to define more points. So we recall that this X has this property where Bx equals to Cx. We now know that this X lies on the perpendicular bisector of the line BC. But so what? Now we also need to remind ourselves that this point D is on the angle bisector of BAC, which means that if you extend the line AD to meet the circumcircle of triangle ABC, then it will be at M, where M is the midpoint of the arc BC, and it just turns out that M is BM equals to MC because M is on the midpoint of the arc, and therefore you have X and M lie on this perpendicular bisector. And finally, if you define another point which is N, where Mn is the diameter of the diameter of the circle containing A, B, and C, then N is also on this perpendicular bisector. So X, M, and N are all on this same perpendicular bisector of the line BC. Now with this thing, we can have a bit more clue, and we can make more claims. So we want to claim that the points X, N, A, and Z lie on the same circle, and this is no longer hard because we already have this xz equals xzza, the angle equals to the angle BCDA. And once we do a bunch of other angle chasing and realize that this XN and XNBC, meaning that this perpendicular bisector, these two are perpendicular, and also DA and DANA. Where was the DANA? These two are also perpendicular because MN is the is A diameter. Then we know that this is pretty immediate. And with this we can remove E in the sense that in the sense that we can redefine the point Z as the intersection of the circle X and A, and also ADC that is not A. Now coming to the point Z again, we also want to make another good use of the of point Z. So why does it so? Now if you look back at this diagram, we would also realize that the point B seems to be a bit weird, because a lot of the points here are defined based on point C, and E is also part of AC. So there are a lot of information that lies on C and also the line AC, but B seems to be a bit out of place, especially after we remove the point F. So one motivation for us is that we might want to remove the point B. So now what? Now that we already have that TD is tangent to DBC, and we want to show that TD and TD equals to TZ, there are a lot of other equivalent things, meaning that we want to show that TZ is tangent to the circumcircle of ZBC. D and Z, which means that D and Z lie on the same Apollonian circle, and therefore it has to satisfy this DB to DC, that the ratio is the same as ZB to ZC. So all these are equivalent, and if we can prove just one of them, we are done. Now the issue is that how are we going to get the length of ZB? This is also one motivation we want to get rid of the point B, because this from here we don't even know how it's not even clear how to get the length of line ZB. But there's also one other tool that we can use to evade. So on this next slide, we see that all we need to do is to rearrange this inequality. So all these out, by the way, are also the same, which means that once we have this equality, we can move to this new equivalent of the problem. So let's say meaning that if Q is the intersection of the line ZD, and also the tangent to C tangent at C to the circle ZDC, then this line BQ should also be tangent to the circle BDZ, and this will also be equivalent to the claim that QB equals to QC. And recall that MN is the perpendicular bisector of the line BC. This means that this is also equivalent to the claim that Q lies on MN. Or you can also say that the line DZ, MN, and also the tangent to DC to the DCZ at C are concurrent. So this means that we can effectively get rid of B, and now our problem statement turns into something that is completely different. So how does it differ? So recall that we have this line line AD, which is on the basically this line AD is the angle bisector of BAC, but it doesn't matter anymore because we don't know, we get rid of B, and then so now it's simply a line AD, and now we also want to define the other points C, M, and N, such that these 4 points N, M, AC are all on the same circle, and MN is the diameter. Now we also have this AC intersect MN and at X. Well, X was the point where XB equals to XC, and therefore on the line MN the perpendicular bisector. And then Z, as we mentioned before, we can turn it into the second intersection of X and A, and also ADC. And then and finally let the line DZ and MN, yes, DZ and MN intersect at Q, and we want to prove that QC is tangent to circle this circle ADC. Now this one is less beautiful compared to the original problem, but it's more useful and easier to deal with because you can see that these lines are more closely related to each other. Yeah. Well, if you look at this one, we need to prove that QC is tangent to the circle ADC. This is also the same as showing that MN, the line MN, the line DZ, and also the tangent to C at C to this circle are concurrent. So this might be more useful to deal with. So this now it doesn't look get trivial either, but and this part of despite how simple it should look, it surprisingly took me a while in order to figure things out. So if there's any cleaner solution that you can think of, feel free to comment on the thread. But the thing is that now that we have a lot of cyclic quadrilaterals, we'll just do something that we are also always good in, which is angle chasing. But angle chasing won't get us anywhere. So there's one new tool that we can introduce, which is similar triangle. So how does it work? Let's say you have two triangles ABC and DEF. If they are similar, meaning that A correspond to D, B correspond to E, C correspond to F, then we will get that the angle at A is the same as angle at D, the angle B is same as angle E, and the same goes to angle C and angle F, and then the corresponding length are also are also follow the same ratio, meaning that the ratio AB to DE, the ratio BC to DEF, and the ratio AC to DF, they are all the same. But oftentimes we do not have all those information. Luckily, we don't need all those information to show that the triangles are similar. So now we are just going to use two of the criteria in order that we are going to use in the solution later. I.e. two criteria to show that the two triangles are similar. So the first one is the two pairs of equal angles, meaning that if A and D are the same, the angle B and E are the same, then they are similar. Well, this is pretty obvious because if two pairs of angles are equal, then the third pair should also be equal because all triangles have angles at to 180 degrees. The second one might be less obvious, but it also holds, meaning that if you have matching ratio, so let's say AB divided by AB AC is the same as DE DF. AB to AC is the same as DE to DF, or equivalently, AB to DE is the same as AC to DF, and the angle in between, which is angle A and angle D, are also the same, then these two triangles are also similar. Now that we have the similar triangle property, we need to make good use of it. Unfortunately, there isn't any similar triangle that could easily pop up from the diagram, so we might have to add a bit more points. So first thing, we have this triangle DQC where Q is basically the intersection of MN and MN and also the line DZ, and then we also have actually where are we? Okay. So we know that Q is the intersection of the line MN and also the line DZ. We define a new point, meaning that you have this circle DQC. We let it intersect AM again at point R. And then we also define another new point. So you have this point R, and then which means that you can get this triangle. Sorry, not triangle, circle, MLC, and then you let it intersect NM again at S. So now now we have all these. We have two more circles. We can go ahead and do a bunch of like different angle chasing, and that we just and then these are just a lot of angle chasing, which I'm not going to go through one by one. But we end up with this point where AZC equals to RQC, ACZ equals to QCR, and therefore we can deduce that these two triangles are similar. And then now that we have more we have more points like this, we can just do even more angle chasing. Except for this one, we what we have is the what we have is like one pair one pair of equal ratio, as you can see over here. And this one is basically just the equal angle, like one equal angle, which is between the two sides we want to show are the same ratio. So we have one more similar triangle, one more pairs of similar triangles. And finally, this one will give us another pair of similar triangles. So we end up with 3 similar triangles. So now that we have three pairs of similar triangles, what we can do? It just turns out that we can just focus on the last similar triangle, which NEZ and SRQ, which is basically built on the previous two similar triangles, and we just get like SQR equals the same as an NZA and etc. etc. The one thing really important that we can get out of is QR is parallel to XA. Okay, QR parallel to XA. Since QR parallel to XA, we can basically finish the solution by doing even more angle chasing over here, and in the end we get this QCD equals to DZC. So QCD, this one QCD equals to what? DZC. This is precisely the same as saying that QC is tangent to the circle DZC, and we are done. So to close off, the solution I use, they are pretty elementary, meaning that the tools we use are just like, you know, cyclic quadrilaterals, similar triangles, and some other things like Monolous Theorem and also trigonometry. The hard part is to actually figure out like which tool we need to use and how to stitch it into a complete solution. And the other thing is that remember that the flowchart that we talk about, like how I'm going to organize my solution, meaning that there's this step 1, step 2, step 2.1, and also the final step 3. Figuring out this division is also a challenging task because you basically breaking the problem into sub problems, and to put it this way, if the problem itself actually gives you like part A asks you to solve this, part B asks you to solve this, and part C asks you to solve this, then the problem is going to be way easier. So meaning that figuring out this sub problem is also the challenging task, and also something that people need to develop. And as a final remark, I have this solution pushed to GitHub. I believe at least I have it my solution written on out of problem solving. But I just think that it's cool to actually like give a video presentation on how the solution looks like, because I think people might be able to learn better this way, because like you can know like what's the motivation behind, instead of just put just a solution which is already like it's like a I would say a truncated form of only a mathematical logic without actually spelling out the thought process. So if there are any other problems that you think it's cool and you want me to make a video presentation, then feel free to comment below. However, I cannot guarantee that I will actually make this video presentation. First of all, it's because of time constraint, meaning that it actually takes quite a bit of time in order to make this PowerPoint slide and also to record this presentation. And second, I cannot guarantee that I can solve the problems that you might you might have on your mind, especially if they are like the hardest problems on the IMO or maybe Putnam. What I could say is that I'm better in geometry and number theory. So if you give problems in those categories, then there are a higher chance that I can get through those problems and subsequently make a video presentation. Also, one reason I make this presentation is also because this problem tree, I thought it was pretty beautiful. So whether I choose to make a video presentation also depends on the quality of the problem. So if the problem that you give, I mean, no offense, all the like video of the problems are pretty subjective, but if you pose a problem that is like it's like really not nice, then I probably won't be motivated to make a presentation either. So yep, that's all from me.